All right, so why don't we get started? So there is homework two is due. Homework two, which is the Edge, Tinkering with Edges, is due tonight at the usual 1 second before midnight. Okay, so where we last left off, we talked about so-called appearance-based features. And appearance-based features, two aspects of an image that you are depicting is the so-called color and shape. And so color is depicted using the distribution of colors associated with that image. And that can be for a grayscale image, or it can be for an RGB image. And the example we carried forward last time, to jar your memory, is for the RGB color image. And so with the RGB color image, you have the red, the green, and the blue components for that image. So it's an M by N by 3 image, and each slice of that M by N by 3 image is the red, green, and blue intensities. And so you compute a histogram of the red intensity, a histogram of the green intensity, and a histogram of the blue intensity. And for each one of those color components, you're going to compute or calculate a histogram with 10 bins. And so you take each of those 10 bins for the red, the green, and the blue, 10 for red, 10 for green, 10 for blue, and you concatenate them together, and that forms a 30 vector, right? And that 30 vector is your so-called color descriptor. It describes the distribution of red, green, and blue collectively that comprise your color image. And then we also talked about the edge map as a way of describing features, and you can calculate the angle of the edges in the image at each point in the image using the inverse tangent, right, arctan. And so when you do that, you basically get a distribution. If you compute a histogram, say with 10 bins, you get a distribution or a visualization or depiction of the distribution of all the edge orientations in the image. And so the examples we gave were a building, an image of a building on the left, your left, and an image of a set of sunflowers in a field on the right. And so considering the building, well, that's a human engineered structure. And in human engineered structures, we like straight lines and right angles. And you'll see there are a lot of vertical edges corresponding to the sides of the buildings, or the windows, the edges, the sides of the windows. And there are a lot of horizontal edges corresponding to the windows as well as the top of the building. And so if you were to take a histogram of the edge map associated with this building, you're going to get peaks in that histograms corresponding to the bin for 0 degrees and 90 degrees. Or it could be 180 degrees and 90 degrees, depending on your convention. Um, Contrast that with the picture of the sunflowers. You're going to get some color representation. In the sunflowers, you have more yellows and brighter greens, whereas for the building, you have kind of more gray color and darker green that dominates. Nonetheless, for the sunflowers, certainly our color feature descriptor, our 30 vector, is going to be different from the building, representing the distribution of the red, green, and blue components through those concatenated histograms. But if you look at shape for the image corresponding to the field of sunflowers, well, in natural scenes, things tend to be more curved, right? You don't see a square tree, you see a round tree as far as the trunk is concerned. But nonetheless, if we look at that circular portion of the sunflower itself, and you imagine kind of fitting small line segments, tracing the edges around the circumference of that circular region of the sunflower, you'd have roughly a uniform distribution or equal counts of edges at various orientations. And so that manifests itself in a histogram as being a histogram of edges for your edge map that is very close to uniform. You can also consider the petals of the sunflower. Well, absolutely, the petals are curved, and so you're going to get more or closer to uniform representation, or something that's very far away from this bimodal distribution over 0 and 90 degrees that you would see with things like buildings. So certainly, just in these descriptors, you put that 30 vector for the red, green, and blue components concatenated with the 10 vector for the histogram corresponding to shape, and this gives you a 40 vector that describes the so-called appearance of the content of these particular images. Okay. Any questions about this? Does that make sense? Yep. All right. And so we'll now move to abstract this mathematically, because if you're going to mechanize the comparison of images, well, you need some mathematical formalism with which to describe them. And so here we have a 40 vector, and let's abstract that with vector value x sub I here. And x sub I is going to be the ith image vector, right? And it doesn't matter how many images you have. You could have 100 images, you could have 1,000,000 images. It doesn't matter. This is just a way of describing a particular image. So the ith image x sub I, or the vector for the ith image x sub I, could be for the building, it could be for the sunflower, it could be for something entirely different. And so this x vector, excuse me, has a dimensionality. And you can think of this x vector as a point in 40-dimensional space. In the same fashion, you learned about Cartesian coordinates. You said a point in 2 dimensions, or a point on the plane, has the so-called x component and the y component, the first feature or the first coordinate and the second coordinate. Now, in this particular case, each coordinate in this 40-dimensional representation is going to represent a particular feature associated with this image. Now, each one of the bin counts from this RGB, this 40 vector, whether that bin count represents red, green, or blue component, or that bin count represents one of the bins from the histogram associated with the edge map, edge directions, or edge orientations, each one of these positions in the 40 vector is going to have a number. And that number you can think of as the coordinate associated with one of the coordinates among this 40 vector, right? And so this 40 vector is some point in a 40-dimensional space, and therefore it's going to have 40 coordinates, each of which describes some aspect, i.e. it's a feature of the associated image from which it was computed. And so mathematically, we have the ith image vector x sub I, and you notice here with this notation, here we describe on the right-hand side of equality here, we have a tuple, and so the order matters. The first position is the first feature, second position is the second feature, and then that last position is that last feature. So you see here in the index, the subscript here for each feature, for the ith image, and you'll notice here the features are not in bold, right? The vector is in bold. Sometimes you see this arrow notation over the vector to indicate that it's a vector, but in the literature, they often use bold to connote the fact that it's a vector valued quantity. And so here we see unbolded version, and that unbolded version is the actual feature value, which would represent one of the 40 bin counts associated with this appearance-based 40 vector. So here we have x sub I comma 1, x sub I comma 2. Well, x sub I comma 1 represents the first feature for the ith image, right, or the first coordinate associated with the ith image. Likewise, x sub I comma 2 would represent the second feature or the second coordinate. So you'd have x sub I, I3, xi4, xi5, up to and including xi40, which is the 40th and last feature. And so that xi40 would be the bin count for this last position in the 40 vector. xi1 would be the bin count for the first position in this feature vector. Does that make sense? Any questions about this? So there's a one-to-one correspondence in this diagram between a feature and a position in the 40 vector above. I just didn't draw it to scale. There aren't 40 positions in this depiction of the vector. Okay. Any questions? No questions? No? All right. So why do we do this in vector form? Well, we do this in vector form because we want to be able to perform mathematical operations in order to compare images. Now, if you're going to sort images from one another, you need a way to represent them. And if once you can represent them, now you can mechanize or write an algorithm that can effectively group together or cluster or categorize images based on their content. And so each image, excuse me, is represented in this case as a 40 vector or point or vector in 40 dimensions. And that space in which this point or this 4D vector is represented is called feature space. Okay. So let's continue on where we left off and go forward. So for the sake of ease of understanding, I know I just got done talking about 4D vectors using this appearance-based representation, but I'm just going to abstract this, and you can imagine if we were just doing a two-dimensional representation, right? So let's say we counted the number of color pixels, we computed the average color, and let's say we computed the average edge orientation, right? It doesn't matter what x11 and x12 are. And it doesn't matter what x21 and x22 are. We just have the first feature here, x11, of that first image, and the first image is going to be represented in two dimensions as a two vector, and that's going to be the building. So x1 vector is going to be the building, and x2 vector is going to be a representation in two dimensions of the sunflowers. And so we have the first feature for the building, and then we have the second feature, x12, for the building. Likewise, we have the first feature for the sunflowers, x21, and we have the second feature for the sunflowers, x22. Now, it doesn't matter if you have a 4D vector or if you have a 2 vector, but I'm showing you a 2 vector now because I want to make a point about what features are and how you draw comparisons. Okay. Does everyone understand this? Okay, so this is a 2D representation. We have two features for each of these images. Okay, so now let's define our images as these 2D vectors. And so we're going to have two unit vectors, x1 hat, x2 hat, describing our feature axes. And so let's imagine we had x1. We can actually plot this image as a point in this two-dimensional feature space. So we have x1 here, and x1 is a representation of that particular image of the building. Now, if you were to, and we also have x2, which is you can plot, and x2 would certainly be different because the sunflowers look different from the building, and therefore their first feature and their second feature are going to be different. So we have x1 and we have x2 plotted in our two-dimensional feature space representation. And so if we plot them in feature space, well, if we look at the component along the first feature axis here for x1, that would be x11, right? So that's what that first feature means when you represent it in feature space. Likewise, the projection of this x1 vector, its second component, the second feature, is going to be represented as x12, and that's going to be the projection along that second feature axis. And so what that means is that when you represent images in feature space as these vectors, and you plot them in this feature space, you're essentially plotting points in some number of dimensions. Now, because we have two features, we're representing these images as a so-called two-dimensional feature space representation. Does that make sense? Any questions about this? All right, so let's do the same thing with X2, right? We said the colors are different for the sunflowers. We said the shape information, the edge orientations are different. So certainly the first feature and the second feature are going to be different, right? So X2, we plot that in feature space in two dimensions. And its first feature is the projection of that point along the first axis. So you could say it's horizontal component. And you notice I'm not saying X and Y, right? I'm staying away from that because when you go to more than two dimensions, it's really hard to say X and Y. So we always talk about the first feature, the second feature, or the first axis, second axis, because when you're using an index to label these axes, you can go up to arbitrary dimension. Now, certainly on the board, I can easily show you two dimensions or three dimensions, but it's really hard, it's impossible to show you something like 40 dimensions, right? Okay, so we have x21, which is the first feature for our second image, and there's its projection along the first feature axis. And then we have x22, which is the second feature for that sunflower image, and that's going to be the projection of that point on the second feature axis. Does that make sense? Any questions about this? And so the coordinates in feature space are the feature values associated with each of these two vectors. Okay, so why do we do this? We can treat these images as points in two dimensions, And now that they're points in two dimensions, you can also treat them as vectors. If you want to treat them as vectors, you would just draw a ray starting at origin in your feature space and ending that arrow for the ray at the particular points. So you can treat them as points or you can treat them as vectors. Points are vectors, if you didn't know already. Okay, you can also treat these images as vectors in two dimensions. So that means if you had a 40-dimensional representation, each one of these points would be a vector in 40 dimensions, right? Same deal. It doesn't matter how big the dimensionality is. The dimensionality only defines how many features you have to describe what the content of this image is. Okay. Any questions about this? No? So, as vectors, certainly, their projection along each of the axes are the feature values, right? So as points, the coordinates are the features. As vectors, the projection along each axis for that vector are the features. Same deal. All right. So one of the questions you want to ask, let's say, you have a big image library, cell phone cameras and other cameras are all over the place. People take lots of pictures, and it'd be nice, you have thousands of pictures, maybe hundreds of thousands of pictures. It's very easy to accumulate a lot of photographs over the years. You might want to sort them or organize them into categories based on what the content of those things are. Or maybe, perhaps, you assign names to some. Maybe, you write a name, dog, and associate that with certain images. You might want to know, okay, what are all the other images that are similar to this? Well, in order to do things like that, to arrange or to mechanize the sorting, categorization, and arrangement of images based on the content, now the question you need to ask is how different are these images? Okay, well, the reason for posing them as points in feature space is because it gives you all the tools of vector mathematics in order to do operations like make comparisons. So the question then, if you want to know how different or similar are these two images, the building from the sunflowers, it's just a question of what the distance is in terms of vector distance between the 2 points, x1 and x2, in feature space representation for image for the building and image for the sunflower. So if you had another image of a building that was very similar to the first one, it's more likely going to be someplace nearby x1. If you had another image of a sunflower in the field that was relatively similar to the second picture on the right, it's going to be somewhere closer distance-wise to x2. And so by taking vector distance between 2 points in feature space, that's how you compare the content between two images to determine if they're similar to one another. Does that make sense? Any questions about this? Okay. So, of course, you're going to use the Euclidean distance, right? The Pythagorean theorem is just an example of Euclidean distance, and this carries in more than 2 dimensions, right? And so you have the distance between 2 points, P and Q, is just you take each one of the components, each one of the coordinates, and you take the difference squared, you sum them together, those differences squared, and then you take the square root of it. It's also called the L2 norm. It's called L2 because you're dealing with a power of 2. 1/2 power is the square root, and the square is to the 2 power. And so this is called the L2 norm, which is what your Euclidean distance is. Now, of course, this works in more than 2 dimensions. You call it the Pythagorean theorem in 2 dimensions, but it's called Euclidean distance in arbitrary number of dimensions. Okay? Any questions about this? So then using this distance measure, and that's not the only distance measure, there are many distance measures that have certain desirable properties, but it's a popular one. But using a distance measure like this, if you had more than 2 data points, you can now group them together by comparing what is the distance between every 2 points. And those points that have the smallest distance between them, right, those are going to be deemed as being similar to one another. Right? So if you wanted to divide a set of images, maybe you had 10 images, and you want to divide them into 2 groups, you say, okay, well, I look at all the pairwise distances between each of the image. So it'd be n choose 2 different distances, and then you take those distances that are smaller and you put them together as points in the same grouping. right? And that's called clustering. Clustering does something like that. You can also, with these distances or something similar to this, you can do something like classification. So let's say you have, 100,000 images of something, and you have a new image that you don't know what the content is. You can now take that system and say, could you tell me what this image is? It's a dog image, or it's a cat image, or it's a image of buildings, right? You can do classification, this predictiveness, this predictive operation, to try to determine what an image is based on what you know from a large set of images that you've collected in the past, right? And it's all predicated on the ability to make comparisons, draw similarities, if you will, or make comparisons between two images based on their content. And so that's done by composing some sort of distance measure. Euclidean is one of them. There are many others. There's Minkowski, there's Mahalanobis, there's nonlinear stuff, all sorts of stuff. You could get a master's degree just in looking at distance measures between certain types of data. But nonetheless, with this distance measure, it now allows you to compare images to see if they're similar based on the content or very dissimilar based on their content. Okay. Any questions about this? Does that make sense? Okay. And so this semester, for this class, we will have uh, a project where you'll be doing either image classification or image clustering. Okay. As vectors. Another thing you can do with images to draw comparisons, instead of representing them as raw coordinates and taking the distance, you can treat them as vectors. And as vectors, how you measure the difference between vectors is by looking at the angle between them. Two vectors that are very similar to one another are going to have a smaller angle between one another, right? And so to measure distance between vectors, you can use something called the so-called cosine distance, right? And what the cosine distance is, it derives from the dot product. It says if you have two vectors, A and B, the dot product between A and B, A dot B, is equal to the magnitude in the L2 norm sense of A times the magnitude of A times the magnitude of B times the cosine of the angle between them. So then if you take this expression and you divide both sides of equality by the magnitude of A and you divide both sides of equality by the magnitude of B, you get cosine of the angle is equal to A dot B divided by magnitude A, magnitude B, right? And that's the so-called cosine distance. Now, that cosine distance is used quite frequently, and derivatives of it are used quite frequently in a branch of machine learning called natural language processing. And so what they do is you take a document, right? And this is not images, it's documents, and documents have text. And you compute a word histogram of all of the words in that document by first going through some processing, extracting features. And so they take the rules of language and they take a tool called a stemmer, and that stemmer finds the root stem of each word. So the root word for running would be run. Root word for ran would be run. And so you run a stemmer over your document, get the stem words, and you remove what are called the stop words, modifiers like the or that don't add any value in terms of the meaning to this document. Then you compute a word histogram and then use cosine distance to measure the difference between these two documents. And so a lot of times when you relevance rank your documents, right, you type a Google search, what are you doing? You have a search term, a bunch of words, and now you're seeing which document most best satisfies what your search term is. It's doing something called term frequency, or this document vector valued representation, and using cosine distances to draw comparisons. Okay. All right. Any questions about this? So you can use cosine distance as another type of similarity measure, but in this case, you're treating each of these points as vectors in d-dimensional space. Okay. No questions? No. All right. So that's the end of the module for appearance-based representation. And so what I'll do is segue, if there are no questions, into the next module, which will get into introduction, some basics for machine learning. Okay. All right. So there's a video I'd like you to watch, and the module today is based on that video. And what it does is introduces you to some terminology in the architecture of a so-called learning system, right? So there are some key ingredients, and like any system, like an operating system or computer, you have an architecture. So too does a program that quote unquote learns also has an architecture. It has some required components that serve a role and they interact with other required components in order to perform its operation. And so we just got done talking about appearance-based representations. We have color for the color part of the appearance. And in this particular case, we concatenate the bins of the red, green, and blue representation. Now, in this example, each one of these bins, these histograms, has 10 bins, but it doesn't have to be 10 bins, right? Each one could have 20 bins. If each one had 20 bins, the resulting color representation would be a 60 vector instead of a 30 vector. Now, what is the right choice? It depends on what you're after. If you want something that's very, very specific or something that kind of generalizes a little bit, and it'll impact your performance as well. Okay, so that's the color part, and then we can look at the shape. The shape looks at the distribution of edge orientations that you would use a convolution mask to extract. And in this example, again, we have a 10 vector because we have 10 bins for the histogram of edge orientations in the image. You don't have to have 10. If you have 20, you're going to be more specific. You're going to distinguish between minor variations, say, of the sunflower. If you have fewer bins, you're going to not distinguish between minor variations of the sunflower, for example. Okay, and so you can concatenate them together, and when you do that, you get a larger vector, and each one of these larger vectors is a concatenation of the color representation and the shape representation to build your so-called appearance-based vector-valued representation. We talked about the mathematical abstraction for each one of these appearance-based feature vectors, and we use vector notation. The subscript I on this xi in bold represents each one of the images in your data set. And then each one of the coordinates or positions in this vector is a feature in this d-dimensional representation. Okay, so any final questions? Almost said final representations. Any final questions? No? All right. So as a point in d dimensions, the projection of each one of these points along the feature axes is the feature. We can represent them as points and measure distances to compare them, or we can treat them as vectors by drawing a ray from origin to each one of these points and take the cosine distance. Okay, so let's jump in to machine learning. And this is just a high level. And you can certainly take an entire semester or two. In our grad program, we have a machine learning course that I teach and a pattern recognition course. So you can literally spend a whole year just talking about the physics of learning as well as different approaches and considerations when you build end-to-end pipelines. And so we're going to, at a high level today, give you an introduction to the required components of a learner, because when we get into classification and clustering, you're going to need to understand where each component fits in. Okay, so let's begin. Machine learning goes back to the relatively early days of computing, and people sort of started to ponder how we think, right? And so the idea of a machine learning system, you can think about it as kind of a mechanized learning system. Can you describe an algorithm and build a machine that can do what we call learning, right? And so that word learning is pretty curious, right? What does it mean to learn? Well, what is it? What does learning mean to you? What do you think? What does to learn? You learned. What does that mean to you? New information. So you have data and there's new information that you incorporate, right? Okay, but what about that new information? You're able to what? I'm sorry? You're able to use it, process it and use it. Now that use it typically corresponds to this notion of in a new scenario, in a new situation. So let's take, for example, the game of soccer, right? You do all sorts of drills. You kind of do a slalom, you go, side to side, you do all sorts of drills. And then in a game, you see stuff that you never saw in practice. But you're able to use what you did in practice in that new situation. You're able to apply it to new situations because you understand how things work. Okay. So you need data, okay, you need processing, and you're able to use it, right? Okay. So this is a definition. Machine learning is a branch of artificial intelligence, and so computer science is divided into three major subcategories. There's the theoretical side, there's the system side, things like operating systems, networking, and then there's the analytical side, things like machine learning, data mining. So it's a branch of the analytical part of computer science. And it's a science and is concerned with putting together algorithms that allow systems to modify their behaviors as they get data. And the interesting part is the more data they get, the more improved their performance. And sometimes, it means you build artifacts. It's more about the data and machine learning, but sometimes you build artifacts like robots and sensor systems and all sorts of things, clusters, high performance computers in support of this goal, especially if you're dealing with a large amount of data. So there are a lot of examples of machine learning in the wild. And machine learning in the wild, first and foremost, consists of data, right? So we have data here on the left. You have a so-called learning model, right? That's sort of the engine that's doing stuff. And we're going to talk today about what this learning model is and give you some framing example for that. And then, of course, there's an application. Now, if you imagine the top row here, you have web pages. Web pages, they have text, they have images, they have links, all sorts of stuff. It's so-called semi-structured documents. So that's your data for something like a Google search. And Google search is a so-called relevance ranked list of results, right? That's the application. But in the middle for the learning model, well, how they represent the web is using a graph where each node represents a document and the content of that document in some form. Typically, it's term frequency based or vector space representation. And then you have edges representing the hyperlinks, right? And so what Google did, it was one of the first statistical based search engines, and what they did in the original version of the so-called PageRank algorithm, and the paper's still out there, you can Google search it and look it up and read it. They used the in degree, the distribution of in degrees across the web graph to score a web page as being more important or less important. And what does that mean? It means that if more people point to you, you must somehow be more important. And they use this term called discrete degree disparity, right? Now, of course, I don't know what they're using now. Um, Beyond what they published, it's a competitive secret. So if you want to know, then get a job there on the PageRank team at Google, and you'll learn it. Probably be sworn to secrecy, but nonetheless, that's their model. They have an algorithm that runs. They have a mathematical representation, and they perform something in that representation in order to get this ranking of so-called importance of web pages. So there's one application. It has data, it has a learning model, and that allows you to do something, and that's the end application. Excuse me. Now let's take the example down below. It's a very different example. It traffics in a different application, and that's autonomous driving. That includes a bunch of things, such as path planning, the ability to find a route along the road system from point A to point B in the geography, to park, collision avoidance, all sorts of good stuff. Now, this has data, but the data corresponds to all that information streaming in temporally from sensors. So that's video for vision for detecting road signs, detecting lane lines, and things like that. You have LiDAR and radar. Radar gives you speed and bearing. LiDAR gives you accurate measurement of obstacles and landmarks around you, right? So we take all that data streaming in time, and now it's about event detection, right? How to take this temporal information, computing various statistics, trying to come up with certain events that trigger certain behaviors in the underlying processes that together give the ability to drive, right? And so there are two different applications. One is web search and one is autonomous driving, but nonetheless, they have data, they have some representation, and they have algorithms that run over these representations to give you different end applications. But the two have the same ingredients, the data, the model, and that drives that application. Okay? Any questions about this? Make sense? All right, so let's take a look at the so-called anatomy of a learner. Now we're going to talk about the architecture. And so the framing example we're going to use is credit approval. So you're a large bank, and let's say you're building a system, and that system is going to input information, records, and it's going to decide whether or not you're going to extend credit, be that a mortgage or a business loan or what have you, to the person that applied. So on the input side, the data, we have the credit application. And let's say if in the case of a mortgage, you're going to have the person's age, they record the gender, annual salary, the number of years in residence, all sorts of information. Now, from this record, you would certainly comprise a feature vector, where that vector or data point in d-dimensional space represents that particular customer. Now, over time, a lot of customers have come into the bank. Let's say your Wells Fargo, your Bank of America, your WSFS bank here in the Mid-Atlantic. Certainly, you're going to have a lot of information in your historical records that you're going to feed into the system. And the hope is that you're going to take this information, the information you already have, and be able to apply it correctly for some new person, a new record that comes in who um, applies for a loan from the bank. Now, if perhaps this new person, their description, their features are very similar to someone who was a good credit risk, they'll say, aha, you're very similar to this person in terms of this applicant information, and this person was a good credit risk. So we're going to go ahead and say, yes, you're approved for credit. Now, let me ask you, certainly automating is a good thing. Um, why would you, or why would you not, want to automate this process? Any thoughts about that? Okay, so is that a for you would want to or wouldn't? Mm. More than meets the eye. So that means what is on paper isn't reflective of who that person really is. Absolutely. So, for example, you could have somebody who's a multimillionaire, right, and has zero debts and has been there for a long time, but he or she just might be a deadbeat, just doesn't like to pay bills, right? Okay. So that's one of those examples. Or perhaps maybe you have somebody on paper that the salary doesn't seem like it's enough, but their family has been in that area for generations and they've always paid back their debts faithfully. Okay. So absolutely, because their profile on paper might not be reflective of who they are in reality. Okay, so that's another example of an example of why you would not. Why would you want to automate it? Is there an example for why would you? So I'll give you an example. When you automate things, you have a system making a decision. And if the system denies you credit, now in the United States, if you're denied credit, the uh, finance organization is required by law to give you a reason why you were denied, right? And so if someone were denied, you can furnish now some of the internal results of the system. It's because the salary was less than this, or because you moved around too much, or because of this, or because of the other. In addition, when you have an automated system, people get around conversations about bias, whether implicit or explicit, because an algorithm doesn't have bias per se. Well, the data does, but the algorithm doesn't. And so that's a way to kind of align with federal law. You can furnish easy explanations about why someone was denied, in addition to treating every customer the same, because it's the same algorithm running over that data set. Now, certainly in real terms, if somebody is an easy case of approval or an easy case of denial, you let the automated system do it. But if someone is right at the edge, you have that system put that record aside and then have a human evaluate it. And so it's up to you as the organization that deploys such a system decide how you want to use it. But in the real world, if the decision is an edge case, you usually have a human being do it. Okay? All right. Any questions about this? So we have a system, it inputs data, and like the image example, we represent this data as a feature vector. We run it through this system, and it's going to output either approval or denial. Okay. So This is the anatomy of a learner, and not very fancy, but we have a bunch of components. And you'll notice here some of these are drawn in red, and some of these boxes or shapes are drawn in black. The red boxes are things that someone's the red boxes are things that you don't have control over, right? As a scientist, and the black boxes are things you do have control over. So let's take a look at what these things are. So it's thought of that you have this unknown target function, right? And so this unknown target function, f, that's the ideal credit approval function. And you input a vector, and that's that big X. It outputs either +1 if you are approved for credit, or -1, no, if you are denied for credit. Now, of course, it's out there, but the problem is that you don't know what it is. If you know what it is, then you just implement it. But in general, you don't know what it is. Well, let me ask you, do you know what the secret formula is for how they approve for credit or deny credit? No, I don't know either, right? I couldn't tell you. And so we have this unknown target function, and this unknown target function assigns approval or denial, so-called labels, to each one of your applicant records, right? And so here we have so-called training examples, or sometimes it's called in-sample points. These are your historical records. These are the applications and the approval or denial decision for all of the historical data for all the applications of people that have come in to that financial institution. You don't have control over that. Each one of these x's, x1, x2, x3, corresponds to a vector of information from each one of the credit applications, and each one of those y values, y1, y2, y3, etc., is the corresponding approval or denial decision associated with that historical applicant. So you don't have control over the training examples, your historical data, which is given to you. So then you have this thing called the hypothesis set. Now, a hypothesis set is a set of candidate formulas. That's what you have control over. And what this is, it's a type of function. You could say, oh, the set of all degree 10 polynomials, right? It's a function, basically you're making an educated guess about what you believe the form of the candidate of the target function is. So you don't know what the target function is, but you kind of guess, make a good guess. I believe this target function can be defined as a degree 10 polynomial, right? How do you select that? Well, take a machine learning course. But nonetheless, you have this hypothesis set, and this hypothesis set is a set of candidate formulas that you believe would be good descriptions for what the target function is doing when it assigns these approval or denial labels, if you will, to each one of the applicant's data points. Okay? And so you have this other thing called a learning algorithm. You also have control over it. Now, what this learning algorithm's job is to search through the hypothesis set, trying to find some function within the hypothesis set. You can call it a working hypothesis. So the learning algorithm searches through the hypothesis set, trying to find some working hypothesis that most closely mimics the behavior of the target function. Well, how do you measure this mimic idea? Well, we'll get to that. But at this juncture, this learning algorithm looks at the training data, right? The examples, historical data, and it trains each candidate hypothesis. What does training mean? It says, okay, given this historical data, I know how the target function would either approve or deny each one of these applicants. Let me take the first working hypothesis and let me run it over these training examples. What would this working hypothesis say? How closely does it agree with the target function? If it disagrees quite a bit, then I search for it, then I continue searching and consider a new working hypothesis. Now, at some point, I do this enough times in my learning algorithm, I'll arrive upon a best working hypothesis, and I call that my final hypothesis. This final hypothesis, G, we hope is equivalent or very close in mimicking the behavior of this unknown target function, and that's your learned formula. Does that make sense? Any questions about this? All right. So your learning model is your learning algorithm, the method you use to search, along with a hypothesis set, the set of candidate formulas that you consider. And the whole goal is to try to find, after some amount of time, some final best hypothesis that most closely mimics the labeling behavior of that unknown target function. You don't have control over the training examples, the historical data. You don't have control over the target function. You don't know what it is. It's out there, floating out there. But you do have control over your choice of learning algorithm and hypothesis set. And if you do it right, you get a very good final best hypothesis. And good is measured as performing well on brand new data that you have not yet seen, right? Data that's outside of the historical records. That's the new customer that comes in and applies for a mortgage, and you take his or her information off the application as a vector in some high dimensional representation, and then you run it through G, the final best hypothesis. Okay? All right. Any questions about this? Okay. So we also have some other components. There's another piece that you have no control over. This is the population distribution. And this population distribution, P, it was responsible for giving you all of the features in the historical data that you did not have control over. It is also responsible for giving you all of the features for the brand new data points that come in. We also have this thing called an error measure, and this error measure is a distance measure, if you will, that compares the performance of a working hypothesis that you're considering against the ground truth target function. That's how the learning algorithm knows that the working hypothesis very closely mimics what the ground truth unknown target function is doing in terms of assigning these labels, this Y1, Y2, approval denial decisions to each one of these historical records. Does that make sense? Any questions about this? And so this is what the architecture of a learner looks like. And the things in black, the error measure, the learning algorithm, and the hypothesis set, are the only things you have control over. Now, certainly in a machine learning course over the course of a semester, we talk about the physics of the system, namely, what are the interactions and competing forces among these components, and how does that choice of the things you do control impact the relationship among the things that you don't control. Okay? All right. So let's have a simple example to kind of drive this home. Let me do a time check. 10:25, about 20 minutes. So the ingredients. We have an input, and these are credit applications. And from that credit application, let's say you have years in residence and annual salary. That's in 2 dimensions, so D equals 2. So you have your credit applicant data, and the output is going to be an approval or denial output. So approval, you'd say +1, denial, you say -1, right? Doesn't matter specifically what they are, but using +1 and -1 makes it mathematically convenient, and you can automate it. And so you have historical data. These are all of the customer records associated with people who have submitted credit applications to the bank and for whom a decision has been made, whether they're approved or denied. And then you also have a hypothesis set. Okay. All right. You have a class of formulas, and you hope that this class of formulas is going to approximate this unknown target function, which was the entity that provided these +1, -1 labels associated with your historical data. All right. So let's come up with a representation. In this representation, we have our data, and we're going to imagine our data is in D dimensions. And so on the horizontal axis, we have annual salary, and on the vertical axis, we have number of years in residence, right? Those are 2 pieces of information that are asked on a mortgage or loan application. So let's say we have one individual, that first green dot, and let's say that person makes $70,000 a year and has been living in the same residence for 7.5 years. Okay. And let's say we have another person, that person makes $55,000 a year annual salary, and this person has been in residence for 10 years. Okay. We can actually draw that data point. Let's say we have another person who makes $75,000 a year, but that person has been in residence for 15 years in the same residence. And so each data point here represents a customer, our historical data, and their information from the credit application or mortgage application is represented in D dimensions. In this case, it's 2 dimensions. But nonetheless, all that mortgage application information describing a single applicant or single person or customer of the bank is described in D dimensions as a data point. Okay? Any questions about this? So similarly for what we did for the images, we're doing this for credit applications. So we call these vectors. Okay, we have x1, x2, x3. Now certainly we can have an arbitrary number of customers in the bank. A customer can have historically hundreds, thousands, millions of credit applicants. Okay, so if we have a lot of them, we can actually plot all of these points in feature space. And again, the horizontal axis is the annual salary, and the vertical axis is years in residence. So one of the things you'll notice here is we have this geometry or relationship in space among all the data points. Some of these points here, you'll notice, are on the upper right-hand side of this feature space, and those tend to have higher salary and at the same time higher years in residence. Other of those points tend to be closer to origin on the lower left-hand side of this feature space, and those tend to be smaller number of years in residence and smaller salary. Now, some of the points I've colored in green, the green dots, and some of the colors I've colored, some of the points I've colored in red. Now, the red points were the ones in this example who were denied a mortgage, and the green points in this example were those who were approved for mortgage. And so from this example, we have so-called feature space, and when we plot our historical data along with the labeling decision, approval or denial, we get what are called points in feature space. And more specifically, we have what are called in literature point clouds, right? You can imagine a cloud of these different, excuse me, of these different data points in feature space. And the geometry is such, you can kind of see it, that people with a higher salary and higher number of years in residence, longer years in residence, tend to be approved for a mortgage, whereas people with a lower salary and smaller number of years in residence tend to be denied a mortgage. And so one of the things that we're trying to do, if we're going to automate the categorization, is that we want to try to separate the approved people from the denied people, right? And so we're going to need a function to do that, and I'll get to that in a moment. Okay, so any questions about point cloud and feature space? Any questions? Make sense? Okay, so that's just a visualization of all the historical data, and its coloring corresponds to these labels assigned by this target function, which is unknown, but it's out there. Okay? All right, so the target function provides us with the ground truth labels. Red means denied or -1. Green means approved or +1. And you don't have access to the target function. If you know what the target function is, implement it. That's not learning. Learning, you're trying to get the system to find a good description for what is unknown. Okay, so the target function assigns the points to 2 groups. These are approved, the green, and those denied, which are the red. And it can also be thought of as partitioning this feature space into 2 groups, the red group and the green group. So now what we're going to do is we're going to think of a function that can separate this feature space into 2 different groups of point clouds, such that in one group you have the approved people, and in the other group you have the denied applicants. Does that make sense? So let me ask you, what type of function do you think will separate these 2? A circle? No? A line. A line will absolutely separate it. Do you know which line? Some line, right? Okay. Some line will, and it will. Okay. So this function is known as a so-called decision boundary, right? It's a boundary that separates the 2 groups of points such that you can make a decision about something. In this case, it's an approval or denial decision. So we're going to select a family of functions that we believe, in our belief, our assumption, it might be off, it might be spot on, but we're going to select a hypothesis set. And when we select a hypothesis set, we're going to imagine, based on what we think, educated guess, what type of function would be a good decision boundary that can separate this point cloud into two groups that is consistent or very close in mimicking how the target function assigned labels, the green and the red, to those points that were approved and those points that were denied a mortgage. Does that make sense? Okay, any questions? All right, so absolutely we have a line in the plane, a line in two dimensions, right? It's a so-called linear model, right? And a linear model in two dimensions is called a line. In three dimensions, it's a sheet or plane. In more than three dimensions, it's called a hyperplane, right? So when we think about a line, we recall the formula for a line, y equals mx plus b, right? And so we have two parameters for this line. Any line can be described by its slope and its y-intercept, where m is the first parameter, the slope, and the y-intercept b is the second parameter. Okay, any questions about this? So we don't know which line, but we think that some line will closely mimic how this target function has assigned the +1 green and the -1 red labels to each one of these data points, each one of which represents a customer. Okay, so line is defined by two parameters, a slope and a y-intercept. So m is the slope, of course, b is the y-intercept. So here in the upper right of the screen, we're going to define a hypothesis set, right? And so this hypothesis set is not the same as feature space. This hypothesis set, this yellow box, is going to describe all possible lines that we can imagine. We need a way of describing any line in the plane. So we just got done saying a line is defined by these two quantities, the slope and the y-intercept, the slope m and the y-intercept b. So here we have a definition of a hypothesis set. Now, along the horizontal direction here, that's going to represent m. M can be small, m can be large, right? If it's further away from origin, it's large. If it's closer to origin, it's small. If it's to the right, it's positive. If it's to the left, it's negative. That's our slope. This other axis here in our hypothesis set, or our description of a hypothesis set, that represents b, the y-intercept. If it's far away from origin, it's large. If it's close to origin, it's small. If it's up above the origin, it's positive. If it's below origin, it's negative. So that means if I were to choose a dot in this golden box, that dot represents a particular choice of m and b, i.e. a particular line. Does that make sense? Any questions about this? All right, so let's do that. So here's a line, this is dotted blue. It has a slope of 1, so m is 1, and it has a y-intercept of 5, right? You can see it pierces the y-axis at value 5. So here, in this hypothesis space, if we choose 1, 5, that represents the line depicted here in feature space. So for every choice of m and b, we have a different line. Every unique choice of m and b gives us a different line. Okay, well, now we have the question of, is this the best line? The best line is that line that can separate the red points from the green points in a way that it most closely mimics what the target function has done in this coloring. So we don't know what the line is, but we do know how to measure how different this line is, this choice is, from the target function. So let's think about this. Okay, well, here we have a group. This group is the red group. Okay, now on the other side of the line, that green group, you can't have red here. That red is not correct. The green group is on one side of the line. The other side of the line is the red group. All of these reds below the line, those are errors, right? Okay, so what do? We say, that line is not very good. We have a lot of errors. Let's choose a different line. So if we're going to choose a different line, we choose a different value for m and b. So let's do that. So what about this line? This line has a slope of -0.5, right? And a y-intercept of 15. Oh, wait a minute. Let's look at this. Well, on one side of the line, below the line, the red side, we have all red points, okay? And on the upper side of the line, upper half, we have all green points. There are no errors. So it perfectly coincides with the ground truth target function in its labeling. So we stop and say, you know what? Because the errors are 0, we're going to say success, and this is now the final best hypothesis, that particular choice of a line. Does that make sense? All right, any questions about this? And so we don't know really what the line is. So we're going to try different versions of M and B. We start out with some initial version of M and B. It's not very good, a lot of errors. So then we move a little bit, change M and B a little bit. We try again. Oh, still errors. Then we change a little bit. Oh, wait a minute, the error is starting to reduce. So then we move a little bit the value of M and B. And so here, you'll notice this wandering path in my hypothesis set. I'm trying different versions of the line. And as I try different versions or different lines, I notice if I move in a certain direction, the errors start to go down, right? Okay. And so I do that for some number of rounds, and then eventually I settle down at some final spot, some final line that most closely agrees with the ground truth target function. And that's my final best hypothesis that I identified as G in the architecture or anatomy of a learner. Does that make sense? Okay, so essentially, this is a form of function approximation, right? You have control over the hypothesis set. It's a space of functions. You have control over the algorithm, the way in which you search. And those two choices together are going to dictate if your final best hypothesis does well or if it does not do well. Now, this idea of doing well goes beyond just will it mimic this unknown target function. Doing well means that you can get a new customer that you have never seen, quote unquote, out of sample. So here, the red points and the green points are historical data. Now, you hope that you can choose a final best hypothesis by searching through your hypothesis set, such that this final best hypothesis, not only does it agree with this unknown target function, which this particular one does, but it also does well when it sees data that has not been presented to it yet. All right, and that's called performance out of sample. And it's that out of sample performance which is which is called in machine learning generalization error, right? How well does it do when you give it new data? And that's what the goal is when you build a learner, is to build something, bless you, in a way that performs well on new data. And there are rich theories and methods for how you measure that. Okay. Any questions about this? Does that make sense? Okay. So this idea of working well with brand new data is calling generalize as well. It applies well out of sample on data that you haven't yet seen, you being the learning system. Okay? All right. So what do you need to do this? Well, you need a data representation. We talked about feature space. You need a hypothesis set. We mentioned lines on the plane, right? You need an algorithm to search. We didn't really talk about that much, but you need some algorithm, a method for searching. And you also need a measure of how well you're doing, right? That error function. And that's what you use to determine how closely a particular choice of a working hypothesis, a line at any given moment, how closely it coincides with this ground truth target functions labeling. Okay? All right. Any questions about this? Does that make sense? Now, this is all very theoretical, very high level, to show you the different parts. I would need probably a semester and a half to really do it justice. But I really want to show you about things that you can do with data going forward in your careers. Analytics and machine learning-ish type of things are becoming much, much more important. And so I thought minimally for this class, I would expose you to either classification or clustering, but you need to talk about the anatomy of a learner before you can do classification or clustering. Okay. Any questions? Does that make sense? All right, so I think this is a good stopping point. So I'm going to stop there, and we will pick back up with this on Thursday. It's now 10:42, and I will see you then. Okay?